Last time we built a hash index on an append-only log, blazing fast lookups until every key had to live in RAM. Today we ask the next question. What if you have billions of keys, and the hash map itself would eat hundreds of gigabytes of memory? The answer is SSTables and LSM-trees, sorted files on disk, a small sparse index, and a clever write path through a memtable. Start with the design we already know. Every write appends to a log. Set name equals John. Set age equals 23. Set plan equals free. Then age updates to 24, a new line at the end. The old age stays on disk, but we ignore it. In RAM, we keep a hash map. Each key points at the byte offset of its latest value. Name at 0, age at 80, plan at 52. Reads are one map lookup, one disk seek. Beautiful, as long as every key fits in memory. Scale that to 2 billion keys. The values can stay on disk. The keys cannot leave the hash map. Every key needs an entry or you can't find it. At that size, you're looking at hundreds of gigabytes of RAM just for the index. The machine becomes the bottleneck. Putting the hash map on disk doesn't save you either. Random seeks, resizing, collisions. We need an index that stays small even when the dataset is huge. New idea. After we clean things up, store the data sorted by key. Age 24, email john@mail.dev, handle @John. Name John, plan pro, status active. Two properties matter. First, alphabetical order. Second, each key appears once, only the latest value. That file is an SSTable, sorted string table. String is just Google's old name for a key value entry. Nothing mystical. Why does sorting help? Because you no longer need an in-memory pointer for every key. A dense index would list age, email, handle, name, plan, status, and at scale, millions of rows. That's the RAM wall again. Instead, keep a sparse index, only a few signposts. Age at offset 0, handle at 1800, status at 4200. Thousands of index entries can cover millions of keys on disk. Huge RAM savings, but only because the file is sorted, so you know what's between two signposts. Lookup name. Binary search the sparse index. Name sits between handle and status. So jump straight to byte 1800. You don't start at the beginning of the file. Then scan forward a short sorted run. Handle, then name, found, value John. Then you'd stop. You indexed a handful of keys, not millions, and still found the record with one seek, plus a tiny sequential read. Sorting also makes merging easy. Take an older SS table, apple, banana, dog, zebra, a newer one, banana 10, cat, elephant. Walk both with 2 pointers, the same idea as merge sort. Always emit the smaller key. When keys match, keep the newer value, banana becomes 10, and advance both. One sequential pass. No random disk thrashing. You leave with one clean sorted file. Bonus. Sorted keys cluster similar strings. User 1001 through user 1005 share a long prefix. Compression loves that. Smaller SS tables, less disk, less I/O when you read them back. There's a catch. Users don't write alphabetically. Writes arrive as zebra, then apple, then monkey, then dog. You cannot cheaply splice a new key into the middle of a sorted file on disk. Inserting cat between banana and dog means shifting almost everything. That's way too expensive for every set. So we sort in RAM instead. That in-memory structure is the memtable, usually a balanced tree acting like a sorted map. Watch the writes. Zebra lands, then apple. The tree reorders. Apple, zebra. Monkey inserts in the middle. Dog slides into place. Always sorted. Now update apple to 9. In the memtable, we don't append a second apple. We replace the value in place. The key stays once. The latest value wins immediately. Why a tree? Inserts and lookups stay roughly logarithmic. The structure stays balanced as it grows, and because keys are already ordered, when we eventually write to disk, we can dump the whole thing as one sequential SSTable. No mid-file inserts. Under the hood, that tree is often a red-black tree or an AVL tree. We're not unpacking rotations today. That gets its own video. For this story, remember, memtable equals sorted map in RAM, absorbing random writes until it's time to flush. Typical threshold is something like 64 megabytes. Hit the limit, freeze that memtable, and prepare a brand new empty one for the next wave of writes. Flush is almost boring, and that's the point. The memtable is already sorted, so writing it to disk produces an SSTable immediately. One sequential write, then open a fresh empty memtable and keep accepting sets. Old data now lives on disk as an immutable file. New data starts accumulating in RAM again. Reads check newest first. Get dog. Look in the memtable. Maybe the write hasn't flushed yet. Miss? Try the newest SSTable, then older ones down to the oldest. First hit wins because a later write to the same key must override earlier ones. That's why order matters. After hours of flushes, you have many SSTables, and the same key can appear in several of them. Background compaction merges them the way we merged earlier. Sorted merge. Keep the latest value. Drop duplicates. Old files get deleted. One clean SSTable remains. Less space, fewer files to search on the next read. Crash problem. The memtable lived only in RAM. Apple and banana just written. Power dies. Those writes vanish unless we planned ahead. So every write also appends to a write-ahead log on disk, unsorted, cheap, durable. On restart, read the WAL, replay the sets, rebuild the memtable. Nothing lost. Once a memtable has flushed safely into an SSTable, that slice of the WAL can be discarded. One more optimization you'll meet in real engines. Bloom filters. Get elephant that never existed could otherwise open every SSTable. A tiny filter per file can say definitely not, skip, or maybe, then check. No false negatives for keys that exist. Occasional false positives are fine. We're only naming them here. Bloom filters get a full video another day. How do you choose which SSTables to merge? Two classics, size tiered. Small files merge into medium, medium into large. Simple, great for heavy write throughput, though multiple versions can hang around longer. Leveled. Data moves down levels L0, L1, L2. Within a level, key ranges mostly don't overlap. Fewer files to search on reads, more predictable performance, paid for with more compaction work and write amplification. Put the write path together. Append to the WAL for durability. Insert into the memtable for sorted speed. When it's full, flush an SSTable. Files accumulate. Background compaction merges them into fewer, larger ones. Reads walk memtable, then SSTable's newest first. Bloom filters, when you add them, skip the empty shelves. That whole design is an LSM tree, log-structured merge tree. Fast-sorted writes in RAM. Crash safety via the WAL. Immutable sorted files on disk. Compaction to reclaim space and drop old versions. Optional Bloom filters to cut wasted reads. Writes stay mostly sequential, kind to SSDs and HDDs. The dataset can dwarf RAM, and because data on disk is sorted, range queries feel natural. Hash indexes hit a RAM wall. SSTables and LSM-trees climb past it. Next in this playlist, B-trees. the other classic way to keep an on-disk index. Bloom filters and the AVL and red-black trees behind Memtables. Those stories come another day. See you in part 3.